time we looked at what life is, and we saw that there are some different interpretations of what you could consider life to be. But of course, we only have the examples that we deal with here on the Earth. And so I just wanted to mention that there are other ways of looking at life. And so even though we are looking at the possibilities for extraterrestrial intelligence from a human point of view, there may be other forms of life that we can't even conceive of that would affect this probability. But what I want to do is follow along with what is commonly referred to as the Drake equation, in which we look at the probability for the communication with extraterrestrial life. And this kind of extraterrestrial life is what we'll call advanced ET life. And so we might wonder then, well, what is our definition for advanced? Well, we're going to use a convenient definition in which advanced means that the technology has the ability to send and receive radio waves. Okay, now why radio waves? Well, because radio waves are the only kind of wave that can travel through the disk of the galaxy. And so if we look at a side view of the galaxy, in which these are the spiral arms in the disk, and this is the galactic nucleus, then we exist in this portion of the galaxy, and if there were another extraterrestrial civilization, say on the other end of the galaxy, it would have to send that information through the disk of the galaxy. And so without radio communication, all the other forms of electromagnetic waves would be wiped out by traveling through the disk. And so we would assume then that anyone that was trying to communicate with us would be using radio waves. And since we can't go there, our best bet is to listen intelligently in the radio part of the electromagnetic spectrum. Now, NASA got a project funded called SETI, and that project is the search for extraterrestrial intelligence. And so they got $100 million by using the Drake equation. And from that Drake equation, they calculated that there should be about 1 million extraterrestrial civilizations in our galaxy. Of course, when we do our calculation, we're not going to be quite as optimistic as they were, because they were trying to get money from the government, and they succeeded. This is the reason why we are using this criteria for advanced, because if we can't communicate with them, then we don't have the ability to talk about the problem. And so this gives us a convenient definition for advanced that allows us to actually see evidence for extraterrestrial life. And so what kind of evidence would we be looking for? Well, a regular series of radio wave pulses would have no information content associated with it. And so we'd be looking for things like maybe prime numbers, or something that would not have a natural way of being produced. And so we might think of that as being the extraterrestrials' way of saying hello. Okay? And so with that idea in mind, and the idea that they also use this same technique to get money from the government to study extraterrestrials, let's go ahead and look at the Drake equation. Okay, now the Drake equation can be broken up into three separate factors. This is the total probability on the left. And we'll set that equal to an astronomical factor times a biological factor times a sociological factor. And so we need to look at each one in turn. The astronomical is essentially the probability that the planet would have conditions favorable for life. And not just any kind of life, but advanced extraterrestrial life. Okay, so remember, advanced means being able to send and receive radio waves. And so let's look at a few astronomical factors. And as we go through this, we'll try to estimate what we think the probability might be. However, these numbers are not going to be accurate, and as a matter of fact, maybe some of the most inaccurate numbers you'll ever see in your whole life. But we're still, the idea of what factors are necessary is important. And regardless of how the numbers turn out, I think at the end we'll be able to agree that the astronomical probability is very low, meaning that Earth-like planets don't happen all the time. They are very unusual. Okay, and so the first astronomical factor that we can look at is that the planet has to be the right size. So we might wonder then, well, what if it's the wrong size? And what is the right size? Well, we think that an Earth-like size is pretty good because we're here. And so that would definitely be in the range of the right size. But what would happen if the planet is too small? Like, for example, Mars. Well, as we saw before, small planets have a bigger area to volume ratio and cool off more rapidly. And so if the planet is too small, it loses its internal energy quickly. Relatively quickly on an astronomical time scale. And at that point, then, there's no more active processes. And the atmosphere evaporates. Due to solar radiation. And so we don't want a planet to be too small because we've seen what happens to planets like Mars. They lost their atmosphere. Mars lost its internal heating mechanism because it was a small planet with a large area to volume ratio. And then subsequently, all of the water evaporated and the atmosphere evaporated. There was no magnetic field to protect the atmosphere, and so Mars was out of luck. Okay. What if the planet is too big? Well, if the planet is too big, then it will hold on to lighter gases like hydrogen, and you're going to have a mix of hydrogen and helium in the atmosphere, which could be so thick that it would prevent the right kind of an atmosphere from developing. And so this is the case with our outer planets. The hydrogen and helium gas dominates. So you don't get then the right kind of atmosphere for life. Okay, so let me just swing over and finish that up on the left-hand board. This is still part of planet has right size. And we're talking about planets that are too big. The planet is too big. There are other problems, one of them being that the gravity is too strong, and so creatures would be smashed flat. Unless, of course, the planet was completely covered by water. But if that's the case, then you probably aren't going to get an advanced technology anyway, because despite the fact that we've all seen Aquaman, I don't believe it, that you could actually have cities that are working underwater with a power source that comes from electricity. All of those kinds of things don't look probable. Okay? And so the planet then needs to be somewhat Earth-like in its size. And we don't know exactly what the upper and lower limits are on that, but we do think that it has to be within some range of size that isn't too big or too small. Number two, the planet has to be made of the right materials. And by right materials here, I mean materials that are necessary for life. So we need heavy elements, and not just hydrogen and helium. So these would include carbon, oxygen, at least on the Earth, nitrogen, very important. And water. Now, on the Earth, even though we're in the right range of distances for the sun to be right temperature for us, we are at a loss to figure how Earth is able to gather enough water if the Earth is just left to itself. Because it's inside of what we call the snow line, and when you're inside of the snow line, water evaporates. So the Earth then is not in a place where ice can form. And if you don't form planets with ices, water vapor doesn't stick to planets as they're forming. And so you don't get any water. The Earth is completely dried out. So we think that on the Earth, it was Jupiter on its way in, that inward migration that was eventually stopped by Saturn. But as Jupiter spiraled inward, talked about this before in a previous lecture, the snowplow model, essentially Jupiter threw a bunch of ices at the Earth in the inner solar system. And so that then is the reason why we think we have water on the Earth today, is basically it came special delivery from Jupiter. And if Saturn hadn't pulled Jupiter back out, Jupiter would have destroyed the inner planets as it migrated inward toward the sun. But it came in just close enough to sprinkle us with a bunch of ices, and also the other inner planets as well. Okay, and so when we look at the probability then that a planet is not only in the right position, but then also has the water, you have to get that water special delivery from some other source. And so what that tells us is that the likelihood of this happening is somewhat questionable. Okay, and so for number one, planets having right size, I'm just going to, because I don't have any other good information here, I'm going to say 1 chance in 2. And for the planets having the right materials, I'm going to say maybe 1 chance in 5 that it would have the right materials and also be the right size. Number 3, the planets must also be at the right distance from the sun. Or in general from its parent star. So this is what is called the habitable zone. So what you need then is a planet that is not too close, but not too far away. That at just that right distance away so that it gets enough solar energy, but doesn't get too much. And so what happens if it's too close? Well, this is the case with Venus now. Venus is too close. And Venus had all of its oceans evaporate, we believe, remember, before. Its greenhouse effect became a runaway greenhouse effect. And now it has temperatures that are so hot that they'll melt lead. And you get metallic rain, you have a crushing CO2 atmosphere. And so being too close then is not good because you lose all your water. And that means you lose your thermostat mechanism. Now, some people have gone so far as to say that maybe Venus has some kind of microbes floating around in its sizzling hot atmosphere. That is possible, but it's not advanced life. I think we can all agree on that, and that's what we're looking at in the Drake equation. Okay, and so if we're too close, then the water evaporates and things just get too hot for life. On the other hand, if it's too far away, then water freezes and you just have a big ice world. And since we're just big bags of liquid water, about 80% water, I think that we can say that having a world that's completely made out of ice without hardly any liquid water on the surface would be extremely inhibiting to the formation of life.